Hello and welcome to the last video of this section, the importance of autocorrelation. In the previous video we plotted cross-correlation between two variables. In this video we'll use matplotlib to compare two sets of data, and then we'll use autocorrelate both datasets to compare how the correlations visualize patterns in data. Autocorrelation represents the degree of similarity between a given time series and a lagged, that is, delayed in time version of itself over successive time intervals. It occurs in time series studies when the errors associated with a given time period carry over into future time periods. For example, if we are predicting the growth of stock dividends, an overestimate in 1 year is likely to lead to overestimates in the succeeding years. The time series analysis data arise in lots of different scientific applications and in lots of financial processes. Some of the examples include generated reports of financial performance, prices over time, computing volatility, and others. If we are analysing unknown data, autocorrelation can help us detect if the data is random or not. For that, we can use a correlogram. It can help provide answers to questions such as, is the data random? Is the time series data a white noise? Is it sinusoidal? Is it autoregressive? What is the model of this time series data? Here we'll use matplotlib to compare two sets of data. One is a Google day trend of search volume for a certain keyword for 1 year. The other is a set of 365 random measurements with normal distribution. We'll autocorrelate both datasets and compare how the correlograms visualize patterns in data. Here we perform these steps. Import the matplotlib.pyplot module. Import the numpy package. Use a cleaned dataset of Google search volume for a year. Plot the dataset and plot its autocorrelation diagram. Generate the same length random dataset using numpy. Plot the random dataset on the same figure and plot its autocorrelation diagram. Add appropriate labels and grids for easier understanding of the plot. So here's our code, and we're now ready to run this. So as we run this code, it renders this figure which you can see on your screen. Looking at the left-hand side plot, it's easy to spot patterns in the search volume data, where bottom left plot is normally distributed random data, where patterns are not obvious but still might exist. Computing and plotting autocorrelation over the random data, we see that there is a high correlation at 0, which is expected. Data is correlated with itself in no time lag, but going before or after no time lag, the signal is almost 0. So we can safely conclude that there is no correlation between the signal in the original time and any time lags examined. Looking at the real data, Google search volume trend, we can see the same behaviour at 0 time lag, still something we can expect for any autocorrelated signal. But we have strong signals at around 30, 60 and 110 days after the 0 time lag. This indicates that there is a pattern with this particular search term and the way people search for it on the Google search engine. Remember that correlation and causation are two very different things. Correlation is used very often when we want to identify a model for unknown data, and to try and fit data into a model. How data correlates to itself is sometimes a first step to identifying an appropriate model for a dataset we're presented with. This requires more than Python. It requires knowledge of mathematical modelling. Various statistical tests will help us answer these questions. Fantastic! In this section we first understood logarithmic plots, created stem plots, and then we learned to draw streamlines of vector flow. We then stepped ahead to use colour maps, scatter plots and histograms. And finally we dived into the importance of autocorrelation. In the next section we'll dive into some additional information on matplotlib gems.